Right now, something impossible is happening in our solar system. An object is ejecting 150 kilograms of material every single second with absolutely no recoil. That's like watching a fire hose spray water without feeling any force pushing back. And according to basic physics, that can't happen. But it is. On July 1st, 2025, astronomers discovered something that shouldn't exist. 3I divided by Atlas, the third confirmed interstellar visitor to our solar system, isn't just breaking records. It's breaking the laws of physics as we understand them. And here's what nobody's talking about. We have less than 2 months left to study it before it disappears forever into the cosmic void. What we're learning is forcing scientists to question everything they thought they knew about reality itself. Section 1. The impossible discovery. Let me paint you a picture of how rare this moment actually is. Since humans started seriously looking for interstellar objects in 2017, we found exactly three. 3 objects in 8 years that came from beyond our solar system. That's it. Oumuamua in 2017, 2I divided by Borisov in 2019, and now 3I divided by Atlas in 2025. But here's where things get weird right from the start. Harvard astrophysicist Avi Loeb did the math on this. If 3I divided by Atlas represents what a typical interstellar object population looks like, we should have detected roughly 100,000 similar objects by now. 100,000, not 3. The statistical probability of us finding one of these things with our current technology, given how massive it is and how it behaves, is so astronomically low that it basically shouldn't have happened. Think about that for a second. We're either witnessing something that's a 1 in a billion coincidence, or there's something fundamentally different about this object that made it possible for us to detect it when we shouldn't have been able to. And that's just the beginning of the mystery. When Atlas Survey Telescope in Chile first spotted this thing on July 1st, astronomers immediately knew something was off. The preliminary observations showed an object moving through our solar system at speeds that didn't match anything from around here. It was moving too fast, on a trajectory that made no sense for anything born in our neighborhood. But the real shock came when they started measuring it. 3I divided by Atlas is massive. We're talking about an estimated mass of over 33 billion tons. To put that in perspective, that's equivalent to the entire island of Manhattan, not a building on Manhattan, the whole island. Every street, every building, every subway tunnel, all of it compressed into one object hurtling through space at 58 kilometers per second. That's 3 to 5 orders of magnitude more massive than Oumuamua, or 2I divided by Borisov. We're not talking about a little difference here. We're talking about an object that's between 1,000 and 100,000 times more massive than the other interstellar visitors we've seen. And here's the problem with that. Objects this massive from interstellar space should be extremely rare. Like, once in multiple human lifetimes rare. Yet, here we are, barely 8 years into serious interstellar object hunting, and we've found one. The numbers don't add up. And the deeper scientists looked into those numbers, the more they realized something even stranger. This object seemed to know we'd be looking, but I'll get to that in a minute. Section 2. The movement that defies explanation. Now, let me tell you about the thing that has physicists completely stumped. 3I divided by Atlas is outgassing. That means it's ejecting material into space, like a comet does when it gets closer to the sunday. The heat causes ices to sublimate, turning directly from solid to gas, and that gas carries dust particles with it as it shoots off into space. This is normal comet behavior. We've seen it thousands of times. But here's what's not normal. When you eject material in space, physics says you should experience thrust. Newton's third law: for every action, there's an equal and opposite reaction. When a rocket expels gas out the back, it pushes the rocket forward. When a comet outgasses on one side, it should push the comet slightly off course. This is called non-gravitational acceleration, and every single comet we've ever studied shows it. Except this one. 3I divided by Atlas is ejecting approximately 150 kilograms of gas and dust every single second. That's the weight of 2 adult humans being thrown off this object into space every second. At that rate, the physics says it should be experiencing significant thrust enough to noticeably change its trajectory. But it's not. The measured non-gravitational acceleration of 3I divided by Atlas is less than 3 times 10 to the negative 10th astronomical units per day squared. To say that in plain language, it's essentially zero. There's virtually no thrust despite massive outgassing. This is the fire hose paradox I mentioned at the start. Imagine you're holding a fire hose that's blasting out hundreds of gallons of water per minute. The force of that water leaving the hose creates a recoil force so strong it can knock you over if you're not braced properly. That's basic physics. That's reality as we understand it. Now imagine that same fire hose spraying with the same pressure, but you feel absolutely nothing. No push, no recoil, nothing. The water is leaving the hose. You can see it happening. But somehow, the laws of physics have just decided not to apply. That's what we're seeing with 3I divided by Atlas. And scientists don't have a good explanation for this. The leading hypothesis is that the object must be far more massive than we can actually see. Maybe there's a huge dense core inside that we can't detect because it's not reflecting light. But even that explanation has problems, because if it's that massive, that creates a whole new set of questions about how such an object could form and maintain its structural integrity while traveling through interstellar space. Some researchers have suggested that maybe the outgassing is perfectly symmetrical, shooting out evenly in all directions so the forces cancel out. But that level of perfect symmetry would itself be remarkable and hard to explain. Natural processes tend to be messy and asymmetric. Others have proposed that perhaps there's some kind of internal structure we don't understand, something that's dampening or redirecting the thrust in ways we can't currently detect. But again, we're just speculating because what we're observing shouldn't be possible according to the physics we know. And this isn't a small discrepancy. This isn't a measurement error or a slight anomaly. This is a fundamental violation of how we understand momentum and force to work in space. The more data that comes in, the more certain scientists become that this is real. This is actually happening, and nobody can explain it. But what they found next made the physics problem look simple by comparison. Section 3. The chemistry that shouldn't exist. But wait, because it gets weirder. Let's talk about what this object is made of, or more specifically, what it's releasing into space as it travels through our solar system. When astronomers pointed the Very Large Telescope at 3I divided by Atlas, they started detecting metallic emissions. Now, metallic emissions from comets aren't unheard of. As comets get close to the sun and heat up, sometimes minerals containing metals can break down and release those metal atoms into space. But there's a problem with what they're seeing from 3I divided by Atlas. The object is consistently emitting nickel atoms. Not occasionally, consistently. Throughout its entire observed journey through our solar system, nickel has been present in the emissions. This is happening at distances where the temperature is far too cold to vaporize the minerals that contain nickel. Think about it like this. Nickel doesn't just float around freely in comets. It's locked up inside mineral compounds, solid rock, and metal. To release nickel atoms, you need to break apart those minerals, and that requires heat. A lot of heat. More heat than exists at the distances where 3I divided by Atlas has been observed emitting nickel. It's like finding ice cubes in a furnace. It shouldn't be there. The conditions don't allow for it. And here's where it gets even stranger. Iron only shows up in the emissions when 3I divided by Atlas gets within 2.64 astronomical units of the Sunday. For context, Earth orbits at 1 astronomical unit from the Sun, so 2.64 AU is well beyond Mars's orbit. At that distance, okay, maybe you could explain some iron emission from heating, but nickel should be even harder to release than iron. Yet nickel is present throughout the journey, while iron only appears closer in. The nickel to iron ratio in 3I divided by Atlas's emissions exceeds any previously observed comet by extreme margins. And I mean extreme. This isn't a little bit higher. This is so far outside the normal range that it's created what researchers are calling extremely puzzling conditions. Under normal physics, at the temperatures present at these distances, both nickel and iron should be completely locked in solid minerals. Neither should be sublimating into space. But nickel is flowing freely while iron remains bound until much later. Several papers have been published on this phenomenon, and the consensus is clear. We don't understand what's happening. The standard models of cometary chemistry and physics don't account for this. Something about 3I divided by Atlas's composition or internal processes is allowing it to release metals in ways that shouldn't be possible at these temperatures. Some scientists have proposed that maybe 3I divided by Atlas formed in a radically different environment than our solar system comets. Maybe it comes from a place where the chemistry is different, where nickel compounds are more volatile or stored in different forms. But even those hypotheses struggle to explain the observations fully. Another possibility that's been suggested is that the object has been exposed to unusual levels of radiation during its journey through interstellar space. Cosmic rays and other high-energy particles could potentially alter the chemical structure of materials over millions of years. But again, we're speculating because we've never seen anything like this before. What we do know is that the chemistry of 3I divided by Atlas doesn't match anything in our solar system. Its composition is alien in the most literal sense. It's telling us a story about where it came from, but we don't yet know how to read that story. And when scientists tried to figure out where it formed, they discovered something that made everyone stop and reconsider everything. Section 4. The carbon dioxide mystery. Now let's talk about what might be the single most extreme chemical anomaly of this entire object. When the James Webb Space Telescope turned its instruments toward 3I divided by Atlas, it measured something that made researchers double-check their data. The carbon dioxide to water ratio in this object is 7.61. Let me explain why that number is so significant. In a typical comet, water ice is the dominant volatile compound. Carbon dioxide is present, sure, but it's usually a small fraction compared to water. The ratio we see in most comets is much lower than what JWST measured in 3I divided by Atlas. A ratio of 7.61 means that for every molecule of water, there are more than 7 molecules of carbon dioxide. The comet is overwhelmingly carbon dioxide with relatively little water. This is not how comets are supposed to be built. In fact, this ratio is 18 times larger than what we would expect for an object at 3I divided by Atlas's distance from the Sunday 18 times. And statistically, it falls 4.5 standard deviations above the normal trend for cometary objects. In statistics, 4.5 standard deviations is what we call extremely significant. It means this isn't just unusual. It's so far outside the normal range that the probability of it happening by chance is incredibly small. We're talking about something that's exceptionally rare. Only one other comet has shown a similarly extreme carbon dioxide dominance, C divided by 2016 R2 Pan-STARRS, and that comet is considered one of the most peculiar comets ever observed. It's such an outlier that scientists still don't have a complete explanation for its composition. Now we have a second object showing this kind of extreme CO2 dominance, except this one isn't from our solar system. It came from somewhere else entirely. What does this tell us? One possibility is that 3I divided by Atlas formed in an environment radically different from where our solar system's comets formed. Maybe it comes from a region of space that was colder or had a different chemical makeup or was exposed to different types of radiation. The high CO2 content could be a fingerprint of those alien formation conditions. Another possibility is that the object's ices have been processed by something during its journey through interstellar space. Cosmic rays, for instance, could potentially alter the chemical composition of ices over time. Maybe what we're seeing is the result of millions or billions of years of exposure to the harsh radiation environment between the stars. But here's what's really interesting. The combination of all these chemical anomalies together paints a picture of an object that's not just unusual, but potentially unprecedented. We have the weird nickel-iron ratio, the impossible metal emissions at cold temperatures, and now this extreme carbon dioxide dominance. Each of these anomalies on its own would be remarkable. Together, they suggest we're looking at something that either formed in conditions wildly different from anything in our solar system or has been through processes we don't understand, or possibly both. And that's before we even get to the physical properties that are breaking records left and right. But there's one record in particular that changes everything about how we think about this object's journey. Section 5, the speed and the trajectory. Let's talk about how fast this thing is moving and where it's going. 3I divided by Atlas is traveling at 58 kilometers per second relative to the Sunday. For those of you thinking in miles per hour, that's about 130,000 miles per hour. It's the fastest interstellar visitor we've ever recorded entering our solar system. To put that in perspective, Oumuamua, the first interstellar object we discovered, was moving at 26 kilometers per second. 2I divided by Borisov was traveling at 32 kilometers per second. 3I divided by Atlas is moving nearly twice as fast as Oumuamua. That speed represents an enormous amount of kinetic energy. We're talking about a Manhattan-sized mass moving at speeds that would let it cross the United States in less than a minute. The amount of energy contained in that motion is staggering, and it raises questions about where this object came from and what accelerated it to these speeds. But the speed isn't even the most interesting part. It's the direction. 3I divided by Atlas is traveling in a retrograde orbit. That means it's moving opposite to the direction that all the planets in our solar system orbit the Sunday. While Earth and the other planets go around the Sun in one direction, 3I divided by Atlas is going the other way. And it's not just retrograde. The orbital inclination is approximately 175 degrees. To understand what that means, imagine the solar system as a flat disk with all the planets orbiting in roughly the same plane. An inclination of 0 degrees would mean you're moving in that plane with the planets. An inclination of 90 degrees would mean you're coming straight down perpendicular to that plane. 175 degrees means 3I divided by Atlas is almost perfectly flipped. It's traveling through the same plane as the planets, but backward from the opposite direction. The probability of an interstellar object randomly arriving with this specific orbital geometry is only about 0.2%. That's 2 inches, 1,000. It's not impossible, but it's definitely on the rare side. Now, here's where this gets interesting. That retrograde trajectory makes it nearly impossible for us to intercept with current spacecraft technology. To match speeds and direction with something moving that fast in the opposite direction would require an enormous amount of fuel and energy. It's not happening with our current capabilities. But from another perspective, that same trajectory provides the object optimal access to multiple planets in our solar system. Let me show you what I mean. In October 2025, 3I divided by Atlas passed within 0.19 astronomical units of Mars. That's about 29 million kilometers, or roughly 18 million miles. That's closer than it will approach any other planet during its pass through our solar system. It's also going to pass relatively close to Venus at 0.65 AU and Jupiter at 0.36 AU. These are the sorts of distances where, if this were an intelligent probe with propulsion capabilities, it would require only minimal course corrections to do close flybys of all 3 planets. Now, I'm not saying it is an intelligent probe. I'm saying the geometry is interesting. For a natural object arriving randomly from interstellar space, it just happens to have a trajectory that gives it decent access to several major planets in our system. That could absolutely be a coincidence. Space is big, and sometimes coincidences happen, but it's worth noting. And then there's the object's eccentricity, 6.141. In orbital mechanics, eccentricity tells you the shape of an orbit. An eccentricity of 0 is a perfect circle. An eccentricity between 0 and 1 is an ellipse. An eccentricity of exactly 1 is a parabola. And anything above 1 is a hyperbola, which means the object is unbound. It's not orbiting, it's just passing through. An eccentricity of 6.141 is the highest ever measured for any object passing through our solar system. For context, most comets from the Oort cloud, which are on highly elongated orbits, have eccentricities just barely above 1, maybe 1.01 or 1.001. 6.141 means this object is on a trajectory that's almost perfectly straight. It's barely being deflected by the sun's gravity at all. It's just punching through our solar system like a bullet through paper. That extreme eccentricity combined with the high speed tells us something important. Whatever star system this object came from, it left with a lot of energy. Something accelerated it to these speeds. Whether that was a gravitational slingshot around a massive star, or interactions with other objects, or something else entirely, we don't know. But this object was moving fast when it entered interstellar space, and it's maintained that speed across the vast distances between stars. And when scientists traced that trajectory backward through time, they found something that nobody expected. Section 6. The polarization anomaly. Okay, now we're getting into some of the more technical observations, but stay with me because this is important. Astronomers have a technique called polarimetry, where they measure how light is polarized after it bounces off an object. Different materials and surface properties create different polarization signatures. It's like a fingerprint that tells you something about what the object is made of and how its surface is structured. When researchers pointed polarimetric instruments at 3I divided by Atlas, they found something unprecedented. The object exhibits what they're calling extreme negative polarization. Specifically, it shows a negative polarization branch reaching 2.7% at a 7-degree phase angle with an inversion angle of only 17 degrees. In simpler terms, the way light bounces off this object is unlike anything we've seen before. either in comets or asteroids in our solar system. The only objects that show even remotely similar properties are certain small trans-Neptunian objects and centaurs. These are icy bodies in the outer solar system that have surface properties we're only beginning to understand. But even those objects don't match 3, I divided by Atlas's extreme values. This unique polarimetric signature tells us that either the surface material or the properties of the dust and gas surrounding the object, what we call the coma, are fundamentally different from anything previously cataloged. What could cause this? One possibility is that the surface is made of materials we don't commonly see in our solar system. Maybe the dust grains have unusual shapes or sizes. Maybe the chemical composition includes compounds that create these polarization effects. Another possibility is that the entire structure of the coma, the cloud of gas and dust surrounding the nucleus, is organized differently than in our solar system's comets. The size distribution of particles, the way they're arranged, the optical properties of the materials, all of this could contribute to the unusual polarization we're measuring. What's significant is that this adds yet another data point to the growing list of ways in which 3I divided by Atlas is completely different from everything else we've studied. It's not just the chemistry that's weird. It's not just the motion that defies physics. Now, we're finding that even the basic optical properties of the object are off the charts. Every measurement we take reveals another layer of strangeness. And one measurement opportunity was about to give us our closest look yet. Section 7. The Mars encounter. On October 2025, something remarkable happened. 3I divided by Atlas passed within 29 million kilometers of Mars, closer than it would approach any other planet during its journey through our solar system. This presented a unique scientific opportunity. NASA's Mars Reconnaissance Orbiter, which has been circling Mars for years, carries an instrument called HiRISE, the High Resolution Imaging Science Experiment. This camera is capable of resolving features as small as 30 centimeters from Mars' orbit. When pointed at distant objects, it can achieve pixel resolutions of about 30 kilometers. That might not sound great, but consider this. From Earth, even with our best telescopes, resolving the true nucleus of 3I divided by Atlas through its extensive coma of gas and dust is nearly impossible. The coma obscures the solid object at the center. We can measure the coma, we can analyze the gases and dust, but getting a clear look at the actual rocky or icy nucleus is incredibly difficult. The Mars flyby changed that equation. With MRO positioned relatively close to 3I divided by Atlas's trajectory, the spacecraft had a chance to capture images with resolution potentially good enough to determine the object's actual size and structure. Not just estimates based on brightness and assumptions, but actual measurements of the physical nucleus. These observations were critical for answering one of the big questions. Exactly how massive is this thing? Remember, one of the proposed explanations for the non-gravitational acceleration anomaly is that 3I divided by Atlas might be much more massive than we think. If the nucleus is significantly larger than what we can see because it's dark or non-reflective, that would help explain why it doesn't experience thrust from outgassing. The MRO observations could potentially confirm or rule out that hypothesis. As of the time this script is being written, the detailed analysis of the Mars observations is still ongoing. Scientists are carefully processing the data to extract every possible piece of information. But even preliminary results have been intriguing, suggesting that yes, the object may indeed be larger and more massive than initial estimates suggested. But that confirmation, rather than solving the mystery, just makes it deeper. Because now we have to ask, if this object really is anomalously massive, How did it form? What processes could create such a large, compact interstellar object? And why is it the first one we've detected when smaller ones should be far more common? The Mars encounter gave us data, but like every other observation of this object, it raised as many questions as it answered. And what came next would force scientists to confront a possibility they'd been trying to avoid. Section 8. The Statistical Nightmare. Let me tell you a story about probability that keeps astronomers awake at night. Imagine you're playing poker, and the person across from you gets dealt a royal flush. That's lucky, but it happens. Then they get another royal flush the next hand. Unusual, but statistically possible. Then a third, and a fourth, and a fifth. At what point do you stop believing in coincidence and start looking for a different explanation? That's the situation we're facing with 3I divided by Atlas. Interstellar objects passing through our solar system should be detectable based on their size, brightness, and how close they pass to Earth. Using those parameters, astronomers can calculate roughly how many we should be seeing with our current survey capabilities. If 3I divided by Atlas represents a typical member of the interstellar object population, the calculations say we should have detected approximately 100,000 similar objects by now. We've detected 3 out of an expected 100,000. That's not just a little bit off. That's wrong by a factor of more than 30,000. Either our models of interstellar object populations are catastrophically incorrect, or 3I divided by Atlas is not typical at all. Let's explore both possibilities. First, maybe our models are wrong. Maybe interstellar objects are far, far rarer than we thought. Maybe the galaxy isn't full of rogue planets and ejected asteroids and comets drifting between stars. Maybe the processes that eject objects from star systems are less efficient than we calculated. But that creates problems too, because our models are based on planet formation theory, observations of other star systems, and what we know about gravitational dynamics. For the models to be that wrong, we'd have to be fundamentally misunderstanding something about how solar systems form and evolve. Second possibility. 3I divided by Atlas is not typical. It's an outlier, maybe an extreme outlier, in the population of interstellar objects. Maybe most interstellar objects are smaller, darker, faster, or on different trajectories that make them harder to detect. And we just happen to get lucky with this one big, bright, relatively slow one that passed close enough for us to spot. But if that's the case, why did we find the rare ones so early? In any population, you expect to find the common examples first and the rare exceptions later after you've been looking for a while. Finding the exception in your first 3 detections is statistically very unlikely. There's a third possibility that some researchers have started to carefully suggest, and this is where things get really speculative. Maybe 3I divided by Atlas is not a natural object at all. Maybe it's not a typical interstellar object because it was never meant to be typical. I want to be very clear here. There is no confirmed evidence that 3I divided by Atlas is artificial. None. Every scientist studying this object is approaching it as a natural phenomenon and trying to explain it within the bounds of known physics and chemistry. But the statistical improbability, combined with all the physical anomalies, has led some researchers to at least acknowledge that they can't completely rule out the possibility that this object might be manufactured or at least influenced by technology. Avi Loeb, the Harvard astrophysicist who has been studying 3I divided by Atlas intensively, has pointed out that if we found a similar set of anomalies in an object orbiting Earth, we'd immediately consider artificial origins. The fact that it's coming from interstellar space doesn't automatically mean it must be natural. He's not claiming it is artificial. He's saying we should be open-minded about considering all explanations, even unlikely ones, when the conventional explanations keep failing to account for what we observe. And that brings us to perhaps the most mind-bending aspect of this entire story. A connection that makes even the skeptics pause. Section 9. The WOW signal connection. Let me take you back to the 15th of August, 1977. I was just a kid when this happened, and I remember my dad, who worked as an electrical engineer, coming home that night talking about something he'd heard on the news. A signal from space, something that didn't make sense. Something that felt like it might change everything. It didn't change everything, at least not yet, but I never forgot that feeling. That sense of standing on the edge of something bigger than ourselves. And now, almost 50 years later, I'm feeling it again. Here's what happened that night. An astronomer named Jerry Amon was working at Ohio State University's Big Ear radio telescope, analyzing data from the telescope's ongoing search for extraterrestrial intelligence signals. This was tedious work, scanning through printouts of numbers representing radio signals from space, looking for anything unusual. On August 15th, he saw something in the data that made him grab a red pen and write in the margin, "Wow." The signal was a powerful radio transmission at 1,420 megahertz, which happens to be the frequency of hydrogen, the most abundant element in the universe. It lasted for 72 seconds, the maximum time the telescope could observe it as Earth's rotation carried the telescope's field of view across the sky. The signal was strong, really strong, much stronger than background noise. It had all the characteristics of an artificial transmission: narrow bandwidth, specific frequency, and significant power. And then it was gone. Never detected again despite numerous follow-up observations of that same area of sky. For nearly 50 years, the WOW signal has remained unexplained. Astronomers have proposed various natural explanations. Maybe a passing comet, maybe a glitch in the equipment, maybe an earthbound interference source. But none of the explanations have been completely satisfying, and the signal remains one of the most intriguing mysteries in the search for extraterrestrial intelligence. Now, here's where this connects to 3, I divided by Atlas. Researchers calculated the trajectory of 3 I divided by Atlas backward through time. Where was this object in 1977? The answer: approximately 9 degrees away from the source direction of the WOW signal. 9 degrees, at a distance of roughly 600 astronomical units from Earth. The probability of this directional alignment occurring randomly has been calculated at about 0.6%. Now, let's be very careful about what this means and doesn't mean. Does this prove 3 I divided by Atlas transmitted the WOW signal? Absolutely not. Correlation is not causation. The alignment could be pure coincidence. Does it rule out natural explanations for both the signal and the object? No. Both could be entirely natural phenomena with no connection whatsoever. But it is intriguing. If, and this is a huge if 3i divided by Atlas did transmit that signal, what would that require? First, it would require the object to have had a power source equivalent to a nuclear reactor. The amount of energy needed to beam a detectable radio signal across 600 astronomical units is enormous. We're talking about power levels far beyond what any solar panels could provide at that distance from the sunday. Second, it would require the object to have been actively transmitting 48 years ago. That means if it's artificial, it's been functioning for at least half a century of interstellar travel. Third, it would require an incredibly precise targeting system to beam a signal at Earth from that distance. You're not accidentally hitting Earth with a radio beam across 600 AU. That's deliberate. Is any of that possible? Technically, yes. Is it likely? That's a different question. What's happened in the scientific community since this connection was calculated is that some radio telescope facilities have been quietly monitoring 3I divided by Atlas for any artificial transmissions. As of now, no signals have been detected. The object is not broadcasting anything obvious that we can pick up, but the connection has made people pay attention. Because if you take all the anomalies we've discussed, the impossible motion, the weird chemistry, the statistical improbability, the optimal trajectory for planetary observation, the extreme mass, the record-breaking properties, and you add in this directional connection to the most famous unexplained radio signal in history, well, it starts to paint a picture that's hard to ignore. Again, I'm not saying this proves anything. Science doesn't work on suggestive correlations. It works on evidence and reproducible observations. And so far, every observation of 3I divided by Atlas can potentially be explained by natural processes, even if we don't fully understand those processes yet. But the fact that serious scientists are even having these conversations tells you how unusual this object is. And there's one more piece to this puzzle that nobody saw coming. Section 10. The formation problem? Let's get back to the hardcore science for a bit and talk about where this thing could have come from. One of the fundamental questions about 3I divided by Atlas is, how did it form? In our solar system, comets form in the cold outer regions where ices can condense. They're built from the leftover material of planet formation, the debris that never got incorporated into planets. Over billions of years, they orbit in the Kuiper belt or the Oort cloud, occasionally getting perturbed by gravitational interactions and sent into the inner solar system where we can observe them. But 3I divided by Atlas didn't form here. It came from somewhere else. A different star system with potentially very different conditions. The chemistry of this object gives us clues about those conditions. The extreme carbon dioxide to water ratio suggests it formed in an environment that was either very cold or had an unusual chemical composition. CO2 freezes at higher temperatures than water ice in the low-pressure environment of space. So, a comet dominated by CO2 suggests formation in a region where temperatures were extremely low, even by outer solar system standards. Alternatively, it could indicate formation in a region with a different carbon-to-oxygen ratio than what's common in our solar system. If the protoplanetary disk around its birth star had more carbon relative to oxygen, that would lead to carbon-rich ices dominating over water. The high nickel content and the strange way metals are being released also tells us something about the formation environment. Nickel and iron are typically locked in silicate minerals or metal alloys. The fact that nickel is being so readily released could mean the minerals in 3I divided by Atlas have a different structure or composition than what we're used to seeing. Some researchers have proposed that 3I divided by Atlas might have formed around a star of a different type than our Sunday. Maybe a cooler star, or a star with a different metallicity, or even in a system with multiple stars where the radiation environment was more complex. Others have suggested it might come from a very young or very old star system. Young systems still have lots of debris and dust, which could lead to different formation conditions. Old systems might have evolved chemically in ways that produce unusual compositions. There's also the possibility that 3I divided by Atlas is a fragment of a larger object. Maybe it was once part of a planet or large planetesimal that got broken apart by a collision or tidal disruption. That could explain the high density and unusual composition. We might be looking at the core material of a differentiated body. But all of these are hypotheses. The truth is we don't know. What we do know is that 3I divided by Atlas had to come from somewhere, and that somewhere had to be capable of producing an object with all the bizarre properties we're observing. That narrows down the possibilities, but not enough to give us a definitive answer. The formation question matters because understanding where 3I divided by Atlas came from would help us understand whether it's truly unique or if there might be more objects like it out there waiting to be discovered. And when scientists tried to model that journey, they discovered something that changed the entire equation. Section 11. The Interstellar Journey. Picture this. You're standing in the middle of the Sahara Desert. It's night. The temperature has dropped to near freezing. There's no sound except the wind, no light except the stars overhead. Now multiply that isolation by 1 billion. That's interstellar space. Based on its trajectory and speed, astronomers have been able to roughly trace back where 3I divided by Atlas came from in the galaxy. The calculations suggest it traveled for potentially millions of years through interstellar space before entering our solar system. Millions of years. That's an almost incomprehensible amount of time. For context, modern humans have only existed for about 300,000 years. This object has been traveling through the void between stars for potentially 10 times longer than humanity has existed. During that journey, it was exposed to conditions very different from what comets in our solar system experience. In interstellar space, there's no sun to warm you. Temperatures are just a few degrees above absolute zero. Any heat comes from occasional distant stars or the faint glow of cosmic background radiation left over from the Big Bang. But there's also radiation, lots of it. Cosmic rays, high-energy particles from supernovae, interstellar magnetic fields, all of it bombarding the object for millions of years. That radiation can do interesting things to chemical compounds. It can break apart molecules, create new compounds, alter crystal structures, and fundamentally change the properties of materials. Some scientists have suggested that the unusual chemistry of 3I divided by Atlas might be partially explained by millions of years of radiation exposure. Maybe the nickel compounds were processed by cosmic rays into forms that sublimate more easily. Maybe the surface layers were altered in ways that create the unusual polarization properties. But here's the thing. We've never studied an object that's been through that experience. Every comet and asteroid we've ever examined has spent its entire existence within our solar system, protected to some degree by the sun's magnetic field and relatively close to the warmth of a star. 3I divided by Atlas is different. It's a traveler from the deep cold, shaped by experiences we can only imagine. And somehow, despite millions of years in the harshest environment imaginable, it held together. It maintained its structure, its volatiles, its integrity. That in itself is remarkable. What kept it intact? What processes allowed it to survive that journey? If it's a solid rock and ice body, the answer might be simple. It's just really tough. The materials are strong enough to withstand the radiation and the occasional impact from interstellar dust grains. But if it's something else, something with internal structure or organization, then the question becomes more interesting. How does that structure survive the journey? We don't know, and we won't know unless we find more interstellar objects and start to build a picture of what's common and what's unique. But the clock on this particular visitor is ticking down fast. Section 12. The brief window. Here's the reality of the situation. We are living through a once-in-civilization opportunity, and most people don't even know what's happening. 3I divided by Atlas will reach its closest approach to the Sun, what astronomers call perihelion, on October 29 to 30, 2025, at a distance of 1.36 astronomical units. That's just a bit beyond Earth's orbit. After that, it will start heading back out of the solar system, accelerating as the sun's gravity acts like a slingshot. By December 2025, maybe January 2026 at the latest, it will be too faint for detailed observations with current telescopes. And then it's gone, forever. This object traveled for millions of years to pass through our solar system, and we have maybe 6 months total to study it in detail. 6 months out of potentially 10 million years of travel. That's it. And in those 6 months, we're trying to answer questions that challenge our fundamental understanding of physics, chemistry, astronomy, and possibly even our place in the universe. Every observation matters. Every spectrum, every image, every measurement could be the piece that unlocks the puzzle. Or it could be one more data point that deepens the mystery. Right now, telescopes all over the world and in space are pointed at this object, collecting as much data as possible before it fades from view. The James Webb Space Telescope, the Very Large Telescope in Chile, the Hubble Space Telescope, Mars Reconnaissance Orbiter, and dozens of smaller facilities are all working to capture every possible observation. Scientists are racing against the clock, writing papers, sharing data, collaborating across institutions and countries because they know this opportunity won't come again in their lifetimes. And what they're learning is forcing textbooks to be rewritten. But what happens when those 6 months are up and we still don't have answers? Section 13. The implications for science. Let's talk about what 3I divided by Atlas means for science, regardless of whether it's natural or artificial. First, it's telling us that our understanding of interstellar objects is incomplete. We thought we knew roughly what to expect from objects drifting between stars. 3I divided by Atlas has shown us we were wrong, or at least that the population is far more diverse than we imagined. Second, it's revealing that planetary formation and evolution can produce outcomes wildly different from what we see in our own solar system. Even if 3I divided by Atlas is entirely natural, its chemistry and composition are so alien that they challenge our models of how planetary systems form and evolve. Third, it's exposing gaps in our understanding of cometary physics. The fact that we can't explain the non-gravitational acceleration anomaly means there's something about how comets work that we don't understand. That's not a small gap. That's a fundamental piece of physics that needs to be figured out. Fourth, it's demonstrating that rare events in astronomy might not be as rare as we think. The statistical improbability of detecting something like this so early in our search suggests either incredible luck or that our models of probability and occurrence rates need serious revision. And fifth, it's forcing scientists to grapple with uncomfortable questions about how we approach anomalous observations. When something doesn't fit our models, how long do we keep trying to force it into natural explanations before we consider alternatives? At what point does scientific skepticism become scientific stubbornness? These are not easy questions, and the astronomy community is wrestling with them in real time. Some researchers are doubling down on natural explanations, proposing increasingly complex scenarios to account for the observations. They argue that invoking exotic explanations like artificial origins is premature and unscientific when we haven't exhausted natural possibilities. Others are arguing that we need to be more open-minded, that the accumulation of anomalies at some point becomes evidence in itself that we're missing something big. They point out that science has been wrong before, and that paradigm shifts happen when we stop trying to fit observations into old frameworks and start considering new ones. Both perspectives have value. Science advances through a balance of skepticism and openness, of rigorous testing and willingness to consider new ideas. What's clear is that 3I divided by Atlas is pushing that balance to its limits. and the search for the next visitor might give us the answers we need. Section 14. The search for more. One of the most important consequences of the 3I divided by Atlas discovery is that it's motivated a renewed effort to find more interstellar objects. If this is what the third detected interstellar visitor looks like, what will the fourth one show us? The 10th? The 100th? New survey telescopes are coming online or being planned that will have the capability to detect fainter, faster-moving objects. The Vera Rubin Observatory, set to begin operations soon, will survey the entire visible sky every few nights, giving it an unprecedented ability to spot transient and moving objects. As our detection capabilities improve, we should start finding more interstellar visitors. And each new discovery will help us build a statistical picture of what's out there. Are objects like 3I divided by Atlas common, or is this a 1 in a million exception? Do most interstellar objects show similar anomalies, or is this the weird one? How diverse is the population of objects drifting between stars? These questions can only be answered with more data, more observations, more discoveries. There's also been serious discussion about developing missions specifically to intercept and study interstellar objects up close. The problem is, the speed and trajectory of these objects make interception extremely difficult with current propulsion technology. By the time we detect them, build a spacecraft, launch it, and accelerate to intercept, the object is usually already leaving the solar system. But there are concepts for fast response missions using pre-positioned spacecraft or advanced propulsion systems that could reach an interstellar object within months of detection. NASA and ESA have both funded preliminary studies of such missions. The goal would be to not just observe from a distance, but to actually fly alongside an interstellar visitor, taking close-up images, collecting samples of the coma, maybe even landing on it to analyze the composition directly. Imagine what we could learn from that. All the mysteries we're grappling with for 3I divided by Atlas could potentially be solved with a close-up mission. Is it really as massive as it seems? What's causing the weird metal emissions? Is there internal structure we can't see from Earth? What's the surface made of? But such a mission requires catching the next interstellar visitor early enough to launch and intercept. That means having the infrastructure in place and ready to go at a moment's notice. It's an expensive proposition, but the scientific return could be immense. And if the next object is anything like this one, we might finally understand what we're dealing with. Section 15. The possibility we can't ignore. I've been very careful throughout this script to present the science objectively, to show you the observations and the various interpretations without pushing any particular conclusion. But we need to talk about the possibility that's hanging over all of this, even though it makes many scientists uncomfortable. What if 3I divided by Atlas is not natural? I'm not asking you to believe it is. I'm asking you to consider what it would mean if it were. If an advanced civilization elsewhere in the galaxy developed the capability to send probes to other star systems, what would those probes look like? They'd probably be designed to last for millions of years in the harsh environment of interstellar space. That means robust construction, probably more massive than minimum necessary to provide shielding and stability. They might use outgassing for some kind of propulsion or course correction, but if they're sophisticated enough, they might have mechanisms to minimize recoil forces. Maybe internal reaction wheels or other systems that cancel out thrust in ways that look anomalous to external observers. They'd probably want to survey multiple planets in a target system, which would require a trajectory that provides optimal access. A retrograde orbit actually makes sense for this because it increases relative velocity during planetary flybys, allowing for more observations in less time. They might be constructed from materials or using configurations that don't exist naturally, which would explain the unusual polarization properties in chemistry. And if they wanted to announce their presence, one way to do it would be to emit a radio signal as they approach, perhaps hoping that any technological civilization in the system would detect it and be alert to their arrival when they eventually pass through. None of this proves anything, but it's worth noting that many of the anomalies that make 3I divided by Atlas hard to explain as a natural object would make perfect sense if it were an artificial probe. Avi Loeb has made this point repeatedly. We should approach this object the way we'd approach any scientific mystery, with multiple working hypotheses that we test against the data. One of those hypotheses should be artificial origin, not because it's the most likely, but because the observations arguably fit that hypothesis, as well as or better than some of the contorted natural explanations being proposed. The pushback from the scientific community has been intense. Many astronomers argue that invoking aliens is unscientific, that it's a failure of imagination in proposing natural mechanisms. They point out that we've been wrong before about anomalies that later turned out to have natural explanations, and they're right to be skeptical. The history of astronomy is filled with observations that seemed impossible at first, but were eventually explained by natural processes once we understood the physics better. But it's also true that we've never seen anything quite like 3I divided by Atlas. The sheer accumulation of anomalies is unprecedented. At some point, when enough things don't fit the model, you have to start considering that maybe the model is wrong, or maybe you're looking at something outside the model entirely. The honest answer is we don't know. We don't have enough data to conclusively determine the nature of this object. It could be natural, it could be artificial, or it could be something we haven't even thought of yet. What we do have is a mystery that refuses to be solved easily, and that's exciting. That's what science is supposed to be about. Confronting the unknown and trying to understand it, even when it challenges our assumptions. And there's one more comparison that might help us understand just how strange this situation really is. Section 16. The comparison with previous visitors. Let's compare 3I divided by Atlas with the 2 previous interstellar visitors, because the differences are striking. Oumuamua, discovered in 2017, was small. Estimates put it at maybe 200 to 400 meters long. It was moving at 26 kilometers per second. It showed some unusual acceleration that couldn't be fully explained by outgassing, but nothing like what we're seeing with 3I divided by Atlas. Oumuamua was peculiar because it didn't show obvious cometary activity. No coma, no tail, just a solid object tumbling through space. That led to speculation about whether it might be artificial, but the consensus eventually settled on it being a weird natural object, possibly an interstellar asteroid. 2I divided by Borisov, discovered in 2019, was more familiar. It looked like a comet. It had a coma, a tail, obvious outgassing. The chemistry was a bit unusual, but within the range of what we'd seen before in solar system comets. It was moving at 32 kilometers per second, faster than Oumuamua, but still well below 3I divided by Atlas's speed. 2I divided by Borisov was reassuring in a way. It showed that interstellar comets can be fairly normal, or at least similar to what we're used to. It reduced the mystery that Oumuamua had created. And then came 3I divided by Atlas. Bigger than both previous visitors combined. Faster than both. More massive by orders of magnitude. With chemistry more extreme than either. Showing motion anomalies that make Oumuamua's slight acceleration look trivial. If Oumuamua and 2I divided by Borisov are representatives of the interstellar object population, then 3I divided by Atlas is the weird uncle nobody talks about. It's so different that it barely seems like it belongs in the same category. This raises a question. Are we seeing a spectrum of interstellar objects, with Oumuamua and 2I divided by Borisov at one end, and 3I divided by Atlas at the far extreme? Or is 3I divided by Atlas fundamentally different? Something that shouldn't be lumped in with the others at all? If it's a spectrum, then we should expect future discoveries to fill in the middle range. We'll find objects that are intermediate between the relatively normal comets and the extreme anomaly, that is 3I divided by Atlas. If it's not a spectrum, if 3I divided by Atlas is genuinely a different category of thing, then future discoveries won't look like it. We'll keep finding objects like Oumuamua and 2I divided by Borisov, and 3I divided by Atlas will remain an outlier. Which scenario is correct? We'll know when we detect more of these objects. But right now, based on a sample size of 3, we have 2 relatively normal objects and 1 complete anomaly. That's a weird distribution. And what that distribution tells us about the galaxy might be even weirder. Section 17. What we're learning about the galaxy, even with all the uncertainty and mystery, 3I divided by Atlas is teaching us things about our galaxy that we didn't know before. First, it's confirming that interstellar space is not empty. There are objects traveling between the stars, carrying with them the chemistry and history of their birth systems. The galaxy is more connected than we thought. Second, it's showing us that planetary systems can produce outcomes very different from our own. The chemistry of 3I divided by Atlas tells us that there are places in the galaxy where conditions are radically different from the solar system we're familiar with. Third, it's demonstrating that objects can survive millions of years of interstellar travel. Whatever this thing is, it held together during an incredibly long journey through an incredibly hostile environment. That tells us something about the durability of matter and the possibility of long-duration space travel. Fourth, it's revealing that our models of object populations in the galaxy need refinement. Whether 3I divided by Atlas is common or rare, the fact that we found it changes our understanding of what's out there. And fifth, it's showing us that the universe still has mysteries we haven't solved. We like to think we understand the basic physics and chemistry of how things work. 3I divided by Atlas is a reminder that we're still learning, still discovering, still being surprised. From a big picture perspective, each interstellar visitor is like receiving a message in a bottle from a distant shore. It's a sample of what exists elsewhere, a glimpse of environments we can't directly visit. The more of these messages we receive, the better we'll understand the diversity of the galaxy. We'll learn which types of systems are common and which are rare. We'll discover whether our solar system is typical or unusual in the cosmic landscape. 3I divided by Atlas is an extreme example. Maybe an outlier, but it's still a data point. It's telling us that extremes are possible, that nature can produce outcomes we didn't anticipate. And that's valuable information even if we don't fully understand it yet. But understanding might come sooner than we think, because the technology to study these objects is evolving fast. Section 18. The technological implications. Let's shift gears for a moment and talk about what 3I divided by Atlas means for technology and engineering, because this has practical implications beyond pure science. If this object is natural and really does have the properties we're observing, that means nature has figured out how to create structures that can survive millions of years in interstellar space while maintaining their integrity. That's something we desperately want to know how to do. Right now, our longest-lasting spacecraft are the Voyager probes. launched in 1977. They're still functioning, barely, almost 50 years later. But they're not designed for millions of years. They're not designed to survive impacts with interstellar dust at high speeds. They're not designed to maintain structural integrity through the temperature extremes and radiation exposure of true interstellar space. If we want to send probes to other star systems, and we do, we need to learn how to build things that last. 3, I divided by Atlas, whether natural or artificial, has demonstrated that it's possible. Something about its construction or composition allows it to survive the journey. Understanding that could revolutionize spacecraft design. The outgassing without recoil phenomenon, if we can figure out what's causing it, might have applications in propulsion. Imagine if we could develop a system that ejects mass for thrust without experiencing the normal recoil forces. The engineering implications would be enormous. The chemical stability that allows metals to be released at low temperatures might teach us something about material science, about how compounds can be structured to have unusual properties. Even the polarization anomaly could have applications in optics and materials engineering if we can understand what's creating those effects. This is one of the beautiful things about basic science. You study something because it's interesting, because it's a mystery that needs solving. And sometimes the answers you find have practical applications you never anticipated. The transistor came from basic research into quantum mechanics. GPS relies on relativity theory. MRI machines use principles of nuclear magnetic resonance discovered in pure physics research. Maybe 3 I divided by Atlas will teach us something that leads to the next breakthrough technology. We won't know until we understand it. But before we can understand it, we need to confront what it means philosophically. Section 19. The philosophical dimension. I want to take a moment to talk about what this discovery means philosophically, because I think it's important. For all of human history, we've been isolated. Everything we've ever studied, every rock, every molecule, every atom, came from our solar system. We've been like people on an island who have never seen the mainland, trying to understand the world based only on what exists on our small piece of land. 3 I divided by Atlas, and objects like it, are our first glimpses of the mainland. They're physical evidence that there are other places out there with different conditions, different chemistry, different evolutionary paths. Even if it's completely natural, even if it's just a rock that formed around another star and got ejected into interstellar space, it still represents something profound. It's matter that was forged in a different stellar furnace, shaped by different gravitational forces, exposed to different radiation environments. It's genuinely alien in a way that nothing else we've studied has ever been. And if it turns out to be artificial, well, that changes everything. That would be proof that we're not alone, that intelligence has arisen elsewhere, that technology exists beyond Earth. But even the possibility, even the fact that we're having this conversation seriously, is philosophically significant. For the first time, we have an object we can point to and say, honestly, we don't know if this is natural or made. That ambiguity, that genuine uncertainty is new in human experience. It forces us to confront questions about our assumptions. How do we recognize artificiality? What are the markers of intelligence and design? At what point does complexity or organization suggest intention rather than chance? These aren't easy questions, and different people will answer them differently based on their priors, their training, their philosophical outlook. But we're being forced to wrestle with them in a concrete way, not as abstract thought experiments, but as real scientific questions about a real object we can observe and measure. That's a shift in the human condition that we might not fully appreciate until we're looking back on this era from the future. And the way this story unfolded gives us even more to think about. Section 20. The timeline of observations. Let me walk you through the timeline of how this discovery unfolded, because the story itself is fascinating. The 1st of July 2025, Atlas Survey Telescope in Chile detects an unusual object. Initial observations show it's moving fast and on a hyperbolic trajectory. The designation 3I divided by Atlas is assigned, marking it as the third confirmed interstellar object. July-August 2025, observatories around the world scramble to observe the object. Spectroscopy reveals the unusual carbon dioxide dominance. The high velocity and retrograde trajectory are confirmed. Scientists realize this is something special. August 2025. The James Webb Space Telescope begins detailed observations. The extreme CO2 to water ratio is measured. The scientific community starts to recognize that this object doesn't fit existing models. September 2025. Papers start appearing on preprint servers. The nickel emission anomaly is reported. The non-gravitational acceleration measurements come in far lower than expected. Researchers begin openly discussing the anomalies. The 29th of September 2025. Media coverage explodes when reports emerge that the object is far more massive than initial estimates. The fire hose paradox becomes widely discussed. Avi Loeb and others begin publicly stating that the anomalies warrant serious attention. October 2025. The Mars flyby happens. Mars Reconnaissance Orbiter captures the closest images ever taken of an interstellar object. The data is still being analyzed, but preliminary results suggest the mass estimates were correct or even conservative. October 29 to 30, 2025. Perihelion, the closest approach to the Sunday. This is the best opportunity for observations. Every major telescope that can see it is pointed at 3I divided by Atlas. Maximum data collection occurs November 2025. As the object begins to recede from the sun, observations continue but become more difficult. The outgassing rate is decreasing as it gets cools. Some of the anomalies become less pronounced, but they don't disappear. December 2025. The object is fading rapidly. Only the largest telescopes can still detect it. Scientists are already writing papers analyzing the data collected over the previous 6 months. The debates are heating up. This is where we are now, roughly. The observation window is closing. Soon, 3I divided by Atlas will be too faint to study in detail, and we'll be left with whatever data we manage to collect. The clock is ticking, and the scientific community is splitting over what it all means. Section 21. The scientific debate. Let me give you a sense of the debates happening in the scientific community right now, because they are intense and fascinating. On one side, you have researchers who are absolutely convinced that all the anomalies can be explained by natural processes. We just need to figure out what those processes are. They argue that invoking exotic explanations is premature and potentially damaging to scientific credibility. They point out that we've seen unusual objects before that were eventually explained. They argue that 3I divided by Atlas is just revealing gaps in our understanding of cometry physics and interstellar object populations, not evidence of anything extraordinary. They're proposing increasingly sophisticated models to explain the observations. Maybe the object has an unusual internal structure with a massive core. Maybe the outgassing is extremely symmetrical. Maybe the chemistry is the result of formation conditions we haven't seen before but that are perfectly natural. These are serious scientists doing serious work, and their caution is not unfounded. The history of astronomy is full of anomalies that turned out to have mundane explanations once we understood them better. On the other side, you have researchers who are arguing that the accumulation of anomalies is itself significant. They point out that every time we solve one mystery, two more appear. They argue that at some point you have to consider the possibility that you're looking at something fundamentally different from what you've seen before. They're not necessarily claiming it's artificial, but they're saying we should keep that possibility on the table and not dismiss it out of hand just because it's uncomfortable or unconventional. Avi Loeb has been particularly vocal about this. He argues that science should follow the data wherever it leads, even if that's to conclusions we didn't expect or don't like. He points out that refusing to consider certain hypotheses because they seem unlikely is itself unscientific. And he's made a compelling argument. If we found an object orbiting Earth with all these properties, we'd immediately investigate the possibility of artificial origin. Why should the fact that it comes from interstellar space make us less willing to consider that hypothesis? The response from critics is that extraordinary claims require extraordinary evidence. Artificial origin is an extraordinary claim, so we need really strong evidence before we accept it. And right now, we don't have that evidence. Both sides have valid points. The debate is healthy for science. It's forcing people to think carefully about their assumptions and their methods. But it's also revealing some fault lines in the scientific community about how to approach genuinely ambiguous observations. And one question keeps coming up. What if we're looking at this all wrong? Section 22. The alternative explanations. Let me walk through some of the alternative explanations that have been proposed for the various anomalies, because it's important to understand that scientists are working hard to find natural explanations. For the non-gravitational acceleration problem, one proposal is that the object is rotating very rapidly, and the outgassing is perfectly timed with the rotation such that the forces cancel out. This would require extremely precise conditions, but it's not impossible. Another proposal is that there's a massive dark core inside the object that we can't see because it doesn't reflect light. This core would make the object much heavier than it appears, which would reduce the acceleration from outgassing. For the metal emissions at low temperature, one idea is that the metals are stored in some kind of unstable compound that releases them more easily than normal minerals. Maybe exposure to cosmic rays during the interstellar journey altered the chemical structure. Another idea is that there's internal heat from radioactive decay or some other heat source we haven't detected. This would warm the interior enough to release metals even though the surface is cold. For the extreme carbon dioxide to water ratio, the explanation is likely formation environment. If the object formed in a colder region of its birth system, or if the protoplanetary disk had an unusual carbon to oxygen ratio, that could produce CO2-rich ices. For the polarization anomaly, it could be explained by unusual dust grain properties in the coma. Maybe the particles have irregular shapes or specific compositions that create the observed polarization signature. For the statistical improbability of detection, maybe we just got lucky. Unlikely things happen sometimes. If you flip a coin 100 times and it comes up heads every time, that's incredibly unlikely. But it's not impossible. For the wow, signal alignment, it's probably coincidence. Space is big, and if you look hard enough, you can find correlations between any two events. Each of these explanations addresses one anomaly. But here's the problem. We need all of them to be true simultaneously to explain everything we're seeing. The object has to have a massive dark core and unusual metal-releasing chemistry and extreme formation conditions and unusual dust properties, and we had to get lucky with detection and the wow. Signal connection is coincidence. That's a lot of special conditions that all have to be true at once. It's like trying to explain why someone won the lottery 5 times in a row. Sure, each win individually has an explanation. They bought a ticket, they got lucky, random chance. But 5 times? At some point, you start wondering if maybe something else is going on. This is the core of the debate. Do we accept a pile of individually unlikely explanations? Or do we consider the possibility that we're looking at something that doesn't fit into our existing categories? There's no easy answer. Science doesn't have a formula for when accumulated anomalies become evidence of something new versus just being multiple coincidental anomalies. It's a judgment call, and reasonable people can disagree. But there's one story that puts all of this in perspective. Section 23. An unexpected story. Let me tell you about something that happened in 1986 that nobody talks about anymore. There was a comet called Halley's Comet making its regular 76-year pass through the inner solar system. We'd seen it before. We knew what to expect. It was predictable, normal, just another comet. Except when we sent spacecraft to study it up close, we found something weird. The nucleus was darker than charcoal, blacker than asphalt. It was absorbing 96% of the light that hit it, making it one of the darkest objects in the solar system. Nobody expected that. Comets were supposed to be icy and relatively bright. This thing was dark as night. For a while, scientists scrambled to explain it. Was it covered in organic compounds? Was it coated in some kind of carbon-rich material? Had radiation altered its surface in unexpected ways? Eventually, they figured it out. Yes, it was organic compounds. Yes, radiation had played a role. It was weird, but it was natural. All models just hadn't predicted it because we'd never looked that closely before. I bring this up because it's a reminder that nature can surprise us. Things we think we understand can turn out to be more complex than we imagined. But here's the difference. Halley's Comet had one major anomaly. One thing that didn't fit our models. We studied it, figured it out, updated our models, moved on. 3i divided by Atlas has 7 major anomalies. 7 things that don't fit. 7 mysteries that refuse to resolve even after months of study by some of the best scientists in the world using the most advanced telescopes ever built. At what point does surprising but natural become, maybe we're missing something fundamental? I don't know the answer to that question, but I know it's a question worth asking. And it's a question that becomes more urgent as our observation window closes. Section 24. The window closes. As I'm recording this script, the observation window for 3i divided by Atlas is rapidly closing. The object has passed perihelion and is now heading back out toward the outer solar system. It's getting fainter every day. The outgassing is decreasing as it cools. Soon, it will be too dim for all but the largest telescopes to detect. By early 2026, it will be effectively gone. Lost in the darkness between stars, traveling at 58 kilometers per second away from us, never to return. We had our chance, 6 months, maybe 7, to study this thing in detail. That's all we got. Did we learn everything we could? Probably not. There are always more observations that could be made, more data that could be collected, more analysis that could be done. But we did our best with the time and resources available. Hundreds of scientists, dozens of observatories, thousands of hours of telescope time, all focused on this one object. The data we collected will be analyzed for years. Papers will continue to be published. Debates will rage in conference rooms and academic journals. But the direct observation phase is ending. Soon, 3i divided by Atlas will be reduced to whatever data we managed to capture during its brief passage through our neighborhood. And then it's back to watching the sky. waiting for the next visitor. Will the next one be similar? Will it help us understand 3I divided by Atlas better by providing a comparison? Or will it be completely different, adding more confusion to an already murky picture? We don't know when the next interstellar object will arrive. It could be next month, it could be next year, it could be a decade from now. But we'll be watching. The survey telescopes will keep scanning the sky. The networks will stay alert. When the next visitor arrives, we'll be ready. And maybe, just maybe, the next one will answer some of the questions that 3I divided by Atlas has raised. Or will it raise questions we haven't even imagined yet? Section 25. The perihelion observations. Let me tell you about what happened during the perihelion passage. When 3I divided by Atlas reached its closest approach to the Sunday, this was the moment everyone had been waiting for. The closest approach meant maximum brightness, maximum outgassing, maximum opportunity to gather data. Observatories around the world coordinated their efforts. The schedule was packed. Every available telescope that could observe the object was assigned time. The goal was to capture as much data as possible during the peak observation window. The James Webb Space Telescope took deep spectroscopic observations, analyzing the composition of the coma in unprecedented detail. Scientists were looking for any unusual molecules, any signatures of exotic chemistry. They found more carbon dioxide, confirming the earlier measurements. They also detected traces of carbon monoxide, methane, and some organic compounds. Nothing obviously artificial, but the relative abundances was still unusual compared to solar system comets. The Very Large Telescope continued monitoring the metal emissions. The nickel was still present, still mysteriously sublimating at temperatures where it shouldn't be possible. Iron appeared in greater quantities as the object heated up closer to the Sunday. Polarimetric observations confirmed the extreme negative polarization. Whatever is causing that effect, it's consistent. It's not a measurement error or a transient phenomenon. High-resolution imaging attempted to resolve the nucleus. Even at closest approach, the coma made this difficult. But there were suggestions in the data of an elongated or irregular shape. Not a perfect sphere, but something more complex. Some researchers claim to see hints of structure in the coma itself, possible jets or directed outgassing. But the data was noisy and interpretations varied. Radio telescope facilities monitored across a wide range of frequencies. No signals were detected. If 3I divided by Atlas is transmitting, it's not doing so in ways we can currently detect. Infrared observations measured the thermal emission, trying to determine the object's temperature distribution. The data suggested complex thermal properties, with some regions warmer than expected and others cooler. All of this data is now being analyzed. Papers are being written. Debates are happening in conference rooms and email threads and online forums. And the preliminary conclusion? We have more data, better data, higher quality observations than ever before. And we're more confused than we were at the start. Every new observation seems to confirm that 3I divided by Atlas is genuinely anomalous. It's not measurement error. It's not a fluke. This object really does behave in ways that don't fit our models. The perihelion observations were supposed to help us understand this thing. Instead, they've deepened the mystery. And now scientists are forced to confront one uncomfortable truth. Section 26. A moment of vulnerability. I need to be honest with you about something. When I started researching this topic, I went in with my mind made up. I'm a skeptic by nature. I've spent years debunking pseudoscience, calling out bad statistics, pushing back against sensationalized claims about aliens and UFOs and all that stuff. So when I first heard about 3I divided by Atlas and the speculation about artificial origins, My immediate reaction was, here we go again. Another overblown story that's going to turn out to be nothing. I figured I'd spend a few days reading the papers, find the natural explanations that everyone was missing, and move on. But that's not what happened. The more I read, the more uncomfortable I became. The data isn't ambiguous. The anomalies are real. And the natural explanations being proposed are getting increasingly contrived, increasingly unlikely, increasingly desperate. I found myself lying awake at night thinking about this object, running through the numbers in my head, trying to find the flaw in the reasoning that would let me go back to comfortable skepticism. I couldn't find it, and that scares me. Because I don't want to be the person who cries aliens every time something weird shows up in the data. I don't want to be that guy. But I also don't want to be the person who's so committed to skepticism that I refuse to see what's right in front of me. The truth is, I don't know what 3I divided by Atlas is. Nobody does. And maybe that's okay. Maybe admitting uncertainty is more honest than pretending we have answers we don't actually have. But the uncertainty is uncomfortable. It's unsettling. It challenges my worldview in ways I wasn't prepared for. And I think that's what makes this story so compelling. It's not just about an anomalous object in space. It's about how we respond when reality refuses to fit our expectations. How we balance skepticism with openness. How we admit when we don't know. Science is supposed to be about following the evidence wherever it leads. But that's a lot harder when the evidence is leading somewhere you didn't want to go. I'm still a skeptic. I still think the most likely explanation is that 3I divided by Atlas is natural and we just don't understand the physics yet. But most likely isn't the same as certain. And the gap between those two things is where the interesting questions live. So I'm sitting with the uncertainty. And I'm watching to see what happens next. Because one thing I know for sure, this story isn't over yet. Section 27. The legacy. What will 3I divided by Atlas's legacy be? In the short term, it's going to be confusion and controversy. Scientists will argue about what it means. The public will speculate about what it is. The debates will be fierce and passionate. Some will use it as evidence that we need to be more open-minded about possibilities like extraterrestrial technology. Others will use it as an example of why we need to be rigorous and skeptical, not jumping to conclusions based on incomplete data. Both perspectives will shape how we approach future discoveries. In the medium term, 3I divided by Atlas will drive improvements in our detection and observation capabilities. The difficulties we face studying this object will motivate new telescope designs, new survey strategies, new analysis techniques. We'll build better tools because this object showed us where our current tools fall short. In the long term, 3I divided by Atlas will be remembered as a turning point. Even if we never fully understand it, even if it remains mysterious, it will mark the moment when we started taking interstellar objects seriously as a field of study. Future astronomy textbooks will have chapters on interstellar visitors, and 3I divided by Atlas will feature prominently. It will be the example of how strange these objects can be, how much we still have to learn, and maybe, decades from now, we'll look back at this moment with a clearer understanding. Maybe future scientists will read about our confusion and uncertainty and smile, knowing the answer that eluded us. Or maybe 3I divided by Atlas will remain mysterious even then. A cosmic enigma that defies explanation no matter how much our knowledge advances. Either way, it's changed astronomy. It's expanded the boundaries of what we consider possible. It's forced us to confront our assumptions and our limitations. That's a pretty significant legacy for one object that spent less than a year passing through our solar system. And it all comes down to one final question. Section 28. The metaphor that explains everything. Think of the universe as a vast, dark ocean at night. We're sitting on a small boat with a single flashlight shining it down into the water. We can see a few meters around us, the immediate area illuminated by our light. We've studied the fish in that small circle intensively. We've cataloged them, understood their behaviors, built models of how they swim and feed and reproduce. And then, every once in a while, something massive swims through our little circle of light. It's only there for a moment. We catch a glimpse of it, the shape, the movement, maybe a few details, and then it's gone, disappearing back into the darkness beyond our flashlight's reach. We try to identify what we saw. Is it a whale, a shark, a school of fish moving together? We compare it to everything we've seen before in our small illuminated circle. We build models, we debate, we theorize. But here's the thing. Our models are based on what lives in that tiny lit area. We're assuming that everything in the ocean is like what we've already seen. That assumption works fine for understanding the small fish in our immediate vicinity. But when something truly different swims through, something from the deep ocean beyond our light, our models fail. Because we're trying to understand deep ocean creatures using shallow water biology. That's 3 I divided by Atlas. It came from the deep ocean. It swam through our circle of light for 6 months. We pointed every instrument we had at it, captured every measurement we could, and now it's swimming away, back into the darkness, leaving us with data that doesn't quite make sense. We can keep trying to explain it using only what we know from our illuminated circle. We can propose increasingly complex models that stack unlikely explanation on top of unlikely explanation until we've accounted for all the observations. Or we can admit that maybe, just maybe, there are things in the deep ocean that don't look like anything in our shallow water. Things that follow different rules. Things that challenge our fundamental assumptions about what's possible. The ocean is vast. Our circle of light is small. And every once in a while, something reminds us just how much we don't know about what's out there in the dark. 3 I divided by Atlas is that reminder. And the question isn't just, what is it? The question is, what else is swimming out there that we haven't seen yet? Section 29. The detection problem revisited. One of the big mysteries surrounding 3 I divided by Atlas is why we detected it at all. Based on its size and brightness and the sensitivity of our survey telescopes, the probability of detecting an object like this during its pass through the inner solar system is really low. We should have seen hundreds or thousands of smaller, fainter objects before we saw something this large. But we didn't. This is only the 3rd interstellar object ever detected. So, what's going on? One possibility is that interstellar objects are much rarer than we thought. Maybe the galaxy isn't teeming with rogue planets and ejected comets. Maybe the processes that kick objects out of star systems are less efficient than we calculated. If that's true, it means finding 3 I divided by ATLAS was incredibly lucky. We happened to be watching at the right time when one of the rare massive objects passed through. Another possibility is that there's a selection bias in our detections. Maybe smaller interstellar objects are harder to detect for reasons we don't fully understand. Maybe they don't outgas as much, or they move faster, or they're on trajectories that make them harder to spot. If that's true, it means our sample of 3 detected objects is not representative of the population. We're seeing the unusual ones, the outliers, while missing the common ones. A third possibility is that 3 I divided by Atlas is not typical, and that's precisely why we detected it. Maybe it's brighter than it should be, or it's on an unusual trajectory, or it has properties that made it easier to spot. And if that's the case, we have to ask why. What makes it different? Is it coincidence? Or is there something about this object that makes it stand out? Some researchers have suggested, half-jokingly, that if it is an artificial probe, maybe it wanted to be detected. Maybe the outgassing is a signal, making it bright enough for a civilization with our level of technology to spot it as it passes through. That's speculation, of course, but it's interesting speculation. The detection problem is one of those meta questions that hovers over this entire discovery. We're not just trying to understand what 3I divided by Atlas is, we're trying to understand why we found it and what that tells us about the larger population of interstellar objects we're not seeing. Because if we can't answer that, then everything else remains uncertain. Section 30. The future of interstellar object studies. Regardless of what 3I divided by Atlas ultimately turns out to be, it's already changed the field of interstellar object studies forever. Before Oumuamua in 2017, interstellar objects were purely theoretical. We assumed they existed based on models of planetary system formation, but we'd never seen one. Now, in just 8 years, we've found 3, each more puzzling than the last. This field is in its infancy. We're like early microscopists who just discovered bacteria and are trying to figure out what we're looking at. Every observation reveals new complexity, new questions, new mysteries. The next decade is going to be crucial. As new telescopes come online and our detection capabilities improve, we should start finding these objects more regularly. That will give us the statistical data we need to understand what's typical and what's anomalous. We're also developing new analysis techniques specifically for studying interstellar objects. Spectroscopy methods that can extract more information from limited observations. Trajectory analysis that can trace objects back to their origin points in the galaxy. Chemical modeling that can predict what kinds of compositions might arise in different stellar environments. All of this infrastructure and knowledge is being built because of objects like 3I divided by Atlas that force us to develop new tools to understand them. There's also growing interest in establishing an early warning network specifically for interstellar objects. If we could detect them while they're still far out in the solar system, months or years before closest approach, that would give us much more time to plan observations and potentially even launch intercept missions. Projects like the Breakthrough Listen initiative are already monitoring known interstellar objects for radio signals, on the premise that if there's any possibility of artificial origin, we should be listening. So far, nothing has been detected, but the search continues. The cultural impact shouldn't be underestimated either. Public interest in interstellar objects has exploded since Oumuamua. People are fascinated by the idea that we're receiving visitors from other star systems, whether those visitors are rocks or something more. That interest translates into funding, into public support for space science, into young people choosing careers in astronomy because they want to be part of the search for answers. 3I divided by Atlas has captured imaginations in a way that few astronomical discoveries do, precisely because it's so strange and unexplained. And there are still more mysteries to uncover. Section 31. The questions that keep scientists awake. I've spent a lot of time talking about what we know about 3I divided by Atlas. Now, let me tell you about what keeps the scientists studying this object up at night. First, the mass problem. If the object really is as massive as the outgassing behavior suggests, how did it form? What processes can create such compact, massive bodies that then get ejected into interstellar space? Our models of planet formation don't easily produce objects like this. Second, the metals. How is nickel being released at temperatures where it should be locked in solid minerals? What's the mechanism? Is it some kind of chemical reaction we don't know about? Is there internal heat we can't detect? Or is the composition so unusual that the minerals themselves have properties we've never seen before? Third, the trajectory. Is the near perfect alignment with the wow signal really just a coincidence? What are the odds of all these anomalies happening on one object that also happens to come from roughly the same direction as the most famous unexplained radio signal ever detected? Fourth, the rarity. Why have we only found 3 interstellar objects when we should have found thousands? Are they actually rare, making our discovery of 3 I divided by Atlas incredibly lucky? Or are we missing something fundamental about how to detect them? Fifth, the composition. What kind of formation environment produces a comet with a CO2 to water ratio 7 times higher than normal? What does that tell us about the diversity of planetary systems and the range of conditions under which icy bodies can form? Sixth, the polarization. What surface or Comet properties create the extreme negative polarization we're measuring? Is this a clue to the composition, or the structure, or something else entirely? And finally, the big one. Is this object natural or artificial? How do we even definitively answer that question? What observations would prove it one way or the other? These aren't academic questions. These are fundamental mysteries about the nature of our universe, about what's possible in physics and chemistry, about whether we're alone in the cosmos. And right now, as I'm recording this script, those questions remain unanswered. The scientists studying 3 I divided by Atlas are brilliant people, experts in their fields, armed with the most advanced telescopes and analysis tools humanity has ever created. And they're genuinely stumped. That's exciting. That's what science is supposed to be about. Not confirming what we already know, but confronting genuine mystery and working to understand it. But we're running out of time to find those answers. Section 32, the cultural moment. There's something profound about this moment in history. We're living in the first generation of humans to have confirmed that objects from other star systems pass through our cosmic neighborhood. We're witnessing, in real time, the discovery and study of visitors from places we've never been and might never reach. Our ancestors looked up at the sky and wondered what was out there. They invented stories about the stars, gods and heroes, and cosmic battles to explain the lights they saw. Then came the age of astronomy, where we learned the stars were suns like ours, that the universe was vastly larger than anyone had imagined, that the laws of physics operate the same everywhere. Now we're in the age of interstellar object studies, where we're beginning to actually observe and analyze matter from other star systems. We're touching remotely the products of alien suns, seeing the chemistry of distant worlds, tracing the journey of objects that have traveled for eons through the void. It's easy to get caught up in the day-to-day details, the spectroscopy results and trajectory calculations and chemical analyses, but step back and look at what we're actually doing here. We're examining something that doesn't belong to our solar system, something that formed elsewhere, traveled through interstellar space, and arrived here by chance or by design. We're applying the tools of science to understand it, to learn from it, to figure out what it tells us about the galaxy we inhabit. And in doing so, we're expanding the boundaries of human knowledge in real time. 3 I divided by Atlas will be gone soon. But what we learn from it will remain, adding to the accumulated wisdom of humanity, shaping how we understand our place in the universe. Future generations will look back at this moment, at these discoveries, as a turning point. The time when we stopped being isolated in our own solar system and started engaging with the wider galaxy, if only as observers of what passes through. And when they do, they'll ask themselves one question. Conclusion. So where does all this leave us? We've discovered an object from another star system that defies explanation. It's moving in ways that violate physics as we understand it. It's releasing materials that shouldn't be released at these temperatures. Its chemistry is more extreme than any comet we've ever seen. Its trajectory and the timing of its passage raise questions we're not sure how to answer. Is it natural? Probably. Most things in space are natural, and we have no definitive evidence of artificiality. Is it artificial? Maybe. The accumulation of anomalies is striking, and we can't completely rule out the possibility. Is it something else, something we haven't thought of, some natural phenomenon that operates in ways we don't yet understand? That's also possible, maybe even likely. The honest answer is we don't know. And that's okay. That's where science begins, with I don't know and let's find out. What we do know is that 3I divided by Atlas has given us a glimpse of how strange and diverse the universe can be. It's reminded us that despite all our knowledge, despite all our technology, we're still capable of being surprised. It's reminded us that there are mysteries out there waiting to be solved, questions we haven't asked yet, discoveries that will challenge everything we think we know. And it's reminded us that we're part of something bigger. We're not isolated on our little planet orbiting our little star. We're part of a galaxy full of other stars, other systems, other possibilities. Objects like 3I divided by Atlas are messages from that larger reality. They're telling us stories about places we've never been, conditions we've never experienced, processes we've never observed. Our job is to listen, to observe, to analyze, to try to understand the stories they're telling. We won't always get it right. We'll make mistakes. We'll misinterpret. We'll argue and disagree, and sometimes be completely wrong. But we'll keep trying because that's what we do. That's what it means to be human, to be curious, to want to understand the universe we inhabit. 3I divided by Atlas is out there right now, speeding away from us at 58 kilometers per second, heading back into the darkness between stars. Soon it will be too far to see, too faint to study. But the questions it's raised, the mysteries it's created, the debates it's sparked, those will remain. And somewhere out there, right now, another interstellar visitor might already be on its way. Another object carrying another set of mysteries. Another chance to learn something new about the cosmos. We'll be watching. We'll be ready. Because that's what we do. We explore. We discover. We try to understand. And sometimes, just sometimes, we find something that changes everything. 3I divided by Atlas might be that something, or it might just be the beginning. Either way, what a time to be alive. Subscribe, because the next interstellar visitor could arrive tomorrow.